Welcome back to another problem, and today we will be doing a relative velocity problem. And so let's get right into it. So we have at some time t, point Q, which is right here, crosses point O's horizontal axis with a purely downward velocity, as denoted by v here. If link OP is 0.15 meters long and then link PQ is 0.1 meters long, they want us to determine the angular velocity of link OP. So this orange one here. So yeah, they want what's omega OP? And then we'll give it the vector sign just in case. Okay, so if you can tell from this problem, and how I said earlier, we are going to be using a relative velocity problem. And how these work in plain rigid body kinematics is we choose 2 points on the same rigid body for our 2 particles. So maybe on link OP, we have point O and we have point P. Those are our 2 points. And so thus the motion of one point as seen from an observer translating with the other must be purely circular. And that's because the radial distance is not going to change. And so by recognizing that we have this circular distance with respect to the other point, we can use our relative velocity equations. And specifically, for any 2 points A and B, we would have the velocity of A with respect to B is going to be equal to the angular velocity between the two, and then crossed with the relative radial vector, which would just be r a with respect to b. Okay, maybe I'll just color this something else, so we have a general framework of what we want to work with. Okay, and yeah, so as you know here, since we have this cross product, we do have vector multiplication. So these all are going to be vectors and hence have direction. And so with plain rigid body kinematic problems, omega AB is either going to be, or it's going to be the vector normal to the plane of motion. So just so we're all on the same page with what we're working with here. Okay, so as you can probably guess from this slide and what I just wrote down, we're going to be using that purple equation in this problem. And so that requires us to get some more geometrical data from our problem statement. But let me just set up the basic framework of what we're hoping to develop here. So given that purple equation, we see that we have point P, which is here, and it is related to point O and point Q because it's connected via the orange and pink link to both. And so because we have this relative velocity relationship, we can do something like this. We can say, okay, the velocity of point P with respect to O is going to be equal to omega OP cross R P with respect to O. And similarly, we also know that VP with respect to O is just going to be equal to VP minus VO. And that's just pure relative velocity. So if we combine these two, let me just move that over there. We can see that, so if we equate the two, we can see that VP is going to be equal to V is naught plus omega OP cross RP with respect to O. All right, denote that as 1. And so we can do the exact same thing with P and Q. So we can write velocity of P with respect to Q is going to be equal to omega PQ cross R P with respect to Q. And then VP with respect to Q is going to just be equal to VP minus VQ. We set those two equal to each other, and we can get VP is going to be equal to VQ plus omega PQ cross RP with respect to Q. And I hope that you can see here that now we have two equations for the velocity of point P. And so if we combine 1 and 2, we can see that V naught plus omega P cross RP with respect to O is going to be equal to VQ plus omega PQ cross RP with respect to Q. Okay? Maybe I'll pull up my little box. Maybe that'll be easier to see as we proceed forward. Yeah, so all we did so far was we took our relative velocity equation, we set it up for our problem statement and for our given problem, and then we just set the general framework for what we want to actually achieve. So we know V naught, that's good. We want to find omega OP. We don't know RP with respect to O, but we can find it. We know VQ, they give it to us in the problem statement because VQ is V as given. We don't know omega PQ, and we can find RPQ. So right now we have one equation and two unknowns. So we don't know omega OP, we don't know omega PQ. Okay? But no matter for now, we will just continue on and see what we can work with as the problem proceeds. So next step we want to determine is the different radial vectors, RP with respect to 0, or RP with respect to O, then RP with respect to Q. So we can just write in some geometrical parameters here. I already went ahead and drew out our triangle from the problem statement at this certain time t. And this is just going to be simple law of cosines and law of sines to determine these angles. And the reason that we're going to need these angles is so we can get RP with respect to O and then RP with respect to Q. So if we go ahead and we do 0.10 squared, so this is going to be the law of cosines. And then we'll just plug in our other values. That's going to be cosine theta. We see that theta is going to be equal to 28.96 degrees. Okay? Then if we do the law of sines here, we can calculate the angle for gamma. And we do that, and we see that gamma is about 46.57 degrees. Okay? Now what I'm going to do is I'm just going to draw in a coordinate axes just so we have our sines straight. So I'm going to be calling this positive j hat or positive y, and then positive I hat or positive x. And then positive k hat would be denoted from the right-hand rule. Okay? So we will proceed forward. So let's calculate RP with respect to O. So that's just going to be, let's see here, RP with respect to point O is just going to be equal to 0.15 times cosine theta. That's going to be I hat, and then, not cosine, sine theta, and that's going to be the j hat component. I'll pull my little box up here again too. Okay, and then if we just go ahead and plug that in, we'll see that this is going to be 0.1312 I hat plus 0.0726 j hat. And then if we do the same thing for RP with respect to Q, that's just going to be 0.1 times negative cosine gamma comma sine gamma. And the reason that we have that negative in here is because here, RP with respect to Q, you can see it's actually to the left of Q. So we have a negative I hat to account for. And then we will see that that comes out to be negative 0.0687 I hat plus 0.0726 j hat. Okay? I'll box up these solutions just so we have them for future reference, and then we'll go ahead and start populating our overall equation. Okay? So, I said we know VO, and we do because VO actually is not moving, as you can see here. So this entire term is just going to be 0. Okay? And so now let's take this equation and we'll just start writing with it. Sorry for zooming out so much. This is probably going to be a longer equation. Now, whenever we're doing these relative velocity equations or relative acceleration equations, you know, it's a lot of bookkeeping. So be sure to be consistent with your signs here. And just so we remember, we have this I, J, K relationship where I crossed with J is positive K, K crossed with I is positive J, and then if we did I cross with K, we get negative J and so forth. So if you follow the clockwise convention, you get your positive unit vectors. But if you went the other way, you would get a negative. So we'll just keep that in mind as we proceed here. Okay, so if we take our equation, actually I might just copy this real quick just so I don't have to rewrite it. Although it may have been quicker just to rewrite it, but we'll see here. Okay, cool. There's that. So omega OP, we don't know that, but we'll just leave it in there. And here's another thing too. We know that omega is going to be a vector normal to the plane of motion. So it's going to be in some k hat direction that we don't know. Because we don't know what direction it's actually going to be in, we will just assume that omega p and omega pq are in the positive k hat direction. And if it turns out that the answer is negative, then we know that we chose incorrectly. But it's okay to assume that for now. Okay, so now all we're going to do is some plug and chug. So omega OP k hat cross, this is going to be RP with respect to O, which we have boxed above, 0.1312 I hat plus 0.0726 j hat. And that is just going to be equal to, we have VQ, which is going to be negative 0.5 j hat plus omega PQ k hat cross negative 0.0687 I hat plus 0.0726 j hat. Okay, now we will just do our cross product. So we have k cross with I. It's going to give us positive j. So we'll have 0.1312 omega OP j hat, and then k cross with j is going to give us negative I hat. So we'll have negative 0.0726 omega OP I hat. And that's going to be equal to negative 0.5 j hat. And okay, so we have k cross with I hat. That's going to be positive j hat, but we already have this minus sign here. So that's going to be minus 0.0687 omega PQ j hat plus, so we have k cross with j, it's going to be negative I hat. So actually we'll just get rid of that plus sign. Put a minus in right away, 0.0726 omega PQ I hat. Okay. Now here's the trick we're going to use to solve this problem. So we have some I-hat, J-hats, and everything else, but they're all under this equal sign. So what we can do is we can just collect terms. So with I-hat, we're going to collect all of our I-hat terms. So that's going to be negative 0.0726 omega OP. And what's that going to be equal to? What other I-hats do we have? Okay, we only have one here, which is just going to be equal to negative 0.0726 omega PQ. And as you can probably see now, those scalars are just going to cross out. Oh, yeah. So yeah, they're just going to cross out, and we're going to have omega OP is going to be equal to omega PQ. And I want to note that I dropped the vector notation on the omegas. I hope that's not confusing, but so these actually do have direction. So maybe I'll put them in now. And then for J hat, we're just going to do the same thing. We're going to collect all of our J terms, which is going to be right here, right here, and right here. So we're going to have 0.1312 omega OP is going to be equal to negative 0.5 minus 0.0687 omega PQ. Now we know that omega OP is equal to omega PQ from above. Okay, so all we're going to do is we're going to add that term over and then divide through by its scalar. And this will give us that omega OP is equal to omega PQ is going to be equal to negative 2.50 radians per second. And so that just means that, see my apps come up. Well, that just tells us that because the sign is negative, we actually chose the wrong direction. So it's actually going to be spinning in the negative k-hat direction. But regardless, given that set of equations that we just developed, we were able to determine the angular velocity of link OP, which just so happened to be the angular velocity of link PQ. And so yeah, so that's it for this question. Let's just do a brief summary of what we accomplished, and then we'll be on our way. So again, this was a relative velocity problem for the plane motion of rigid body, and we were analyzing the kinematics. Because we have this relative velocity idea where if it's rotating and we have this circular motion, we can have this purple equation here. And by doing that, and because point P was constrained on both links, OP and PQ, we were able to set those two equations equal to each other from equations 1 and 2. And then we essentially just plugged and chugged with our geometrical data to get equation 3. We found that the two links actually had the same angular velocity at this time, and then we just solved by collecting terms from I hat and J hat, and then being cognizant of our cross product rules. And so yeah, so that's it for this problem. I know it was a bit long, but I think just showing the bookkeeping is useful sometimes, as I did here. And so yeah, I hope this was helpful, and I hope to see you around for the next video. Thank you.